This is Jay Alameda at NCSA. I agreed to host this today, and I'm sorry for the delays as I was figuring out the ins and outs of AT conference. I'm pleased to have two great speakers here today for our symposium. The first one is Ritu Arora from TAC, and her talk is entitled A Short Story of Efficiently Using Two Open Source Applications on Stampede. Without further ado, Ritu, will let you take it away.
Thank you, Jay. Hello, friends. Today I will talk about two of my ECSS projects. One was related to the archaeology domain, and the other one was related to the astrophysics domain. So I will give you a very brief overview of what the project involved and a couple of challenges related to both of the projects and how we surmounted those challenges. They weren't big challenges in the sense that there wasn't too much of work involved, but it was more of like figuring out what to do at the quickest that was challenging. So my first project was related to the exploration and triage of complex archaeological collections. So this project was under the PI from Institute of Classical Archaeology at UT Austin. Her name is Jessica Trilogan, and the project was successfully completed last year in June. So at Institute of Classical Archaeology, what they do is they carry out multidisciplinary archaeological research, conservation, and cultural resource management projects. So they deal with the data from Italy and Ukraine, and they had collected 3 to 4 decades worth of data, and the data collection had changed many hands. So today what they need to do is they need to publish their data to public so that they can, for furthering the scholarly research activities. However, because the data set was so complex and there were a lot of duplicates and there were corrupt files, you name it, and the naming convention was interesting. They had inverted commas, spaces, and various other interesting permutations and combinations of various characters that you can find on your keyboard probably. So in a sense, they were trying to make sense out of their data, and their workflow entailed running a tool called Droid. And Droid, what it does is it profiles all the data, and it creates metadata that can then be visualized using various tools, for example, like Tableau. So the curators were trying to make sense out of their data by deriving metadata, because the whole data collection was more than 4 terabytes at the time of the project. And it was an evolving data collection. So the snapshot of data today would be older, let's say a week from now. And they need to really be moving fast, very fast in the whole process. So what happened was when they were working on their local server, it used to take them more than 2 days to profile just a small subset of data. Think about 2 terabytes from the 4 terabytes that they had to really scan through. And it would take them, besides the time taken, they did not have control to run everything on their own. They had to run it via a system admin if they need to really do it better. So they did not have control on so many things. So eventually they turned to TAC and Exceed for help, and that's how I got involved with the project. And we helped them establish their data management workflow on Stampede, and one of the steps in the workflow was to run multiple parallel instances of the Droid tool that I told you about. So as I said, Droid is used for profiling.
Figure out how to put this on a headset, I would.
So is it sound clear? Hello?
Yes, you're good.
You're fine.
Oh, thank you. So Droid basically stands for Digital Record Object Identification, and as I was telling you, it's used for profiling the data sets. Its unique point, or the nice point, is that there are innumerable formats, like the hundreds and hundreds of formats that Droid can recognize and profile. So what we did was, as the first step, just ran one instance of Droid on Stampede after making it work. There were some tweaks to get Droid working on Stampede at the beginning. But when we got it working, it took like about 6 to 8 hours on a single node on Stampede to profile 4.3 terabytes of data. Now, what they really want to be doing is to like quickly profile as much as possible so that they can visualize as quickly as possible. So time was at a premium so that they can proceed with their publication activities. So then we did some like parallelization. It was like high throughput way. It was not like using MPI or anything. It was more like a launcher type of a job. So we ran multiple Droid instances in parallel on multiple nodes, and we brought down the time from 6 to 8 hours on one node to about 1 hour and 15 minutes on 31 nodes. And I will skip this graph, and I will quickly go to the issues we ran into while we were trying to get Droid run in parallel. So Droid is written in Java, and what it does is, when it has to create the profile of the data collection, it creates a database profile first. And each profile has a unique ID associated with it. So when there were multiple simultaneous Droid runs for distributing the metadata extraction process, we found that the job started crashing due to database conflicts. And it was found that the jobs were crashing or the database conflicts were arising because multiple profiles were getting assigned the same ID. And upon looking into the Droid code, we found that it was using the current system time in milliseconds for generating the seemingly unique profile ID. Henceforth, we ended up with multiple profiles with the same ID and then the crashes and everything. So what we did was very contrary to what a high-performance computing specialist would do. Instead of speeding up the process, we staggered it a little bit. So after finding this bug and few other bugs in Droid, we reported it to the development team, but they were stretched thin on their time to make the fixes, and we were stretched thin on our time to fix the code ourselves and do the regression testing. So we just took this quick fix approach where we staggered the job submission process. So in the sense that first one Droid job would start, then after 5 seconds, another Droid job would start, and so forth. And we could not have done it through one job script because the load balancing here was an issue. We were doing a very coarse-grained load balancing of the amount of data across different nodes, as in it was not that the whole data set was uniformly chunked and each Droid instance worked on a particular set of data which was uniformly distributed. I mean, it was not that all Droid instances got the same size of data set to work with. So the concern of the PI was if we just run it via the traditional batch mode, we will end up spending too many SUs because certain instances might finish in minutes while others might take hours. So what we did was wrote a wrapper bash script that submits multiple independent jobs depending upon the required number of independent Droid runs. So it was a very simple script. All it had was like a step to go to a dummy job script, copy it, and replace the dummy command with the actual Droid command. That is all this wrapper script is doing. And we induced a wait time of 5 seconds so that the profile IDs don't end up being same for different Droid runs. So there was this parameter list file that the user would prepare, and they could either use a script for that or they could manually prepare this file and provide it as an input for the script. And basically that was all. And eventually we just run like one Droid instance per node to overcome challenges related to uneven data distribution and certain droid instances ending up faster than others. So in this script that I'm showing you on the slide currently, you see something as command goes here where my cursor is. So this text command goes here is substituted by the actual droid command that would be used to profile the data set. So as I said, what would happen is the wrapper script would do one job submission, then another. So there would be total 31 job submissions and 31 profile IDs created, which would be unique. So that was the story about running droid on Stampede. But what happens after that is just extracting the metadata and checksum was not enough. They need to really be quickly making sense out of the data. So we recommended using Tableau for information visualization. They could just go and look various, they could develop various views of the data collection using Tableau. So it was interesting that they found that there was gigabytes worth of personal music file that somebody had ended up putting in the data collection. And likewise, there were certain other data that could be considered as noise that they ended up figuring out using information visualization. I will back up a slide and I will go to the slide on the project characteristics. So one of the bottom lines or takeaway messages from this project for me was how to work with non-traditional HPC users and make them productive at what they're doing. So training the stakeholders of this project was one critical aspect. So I trained 2 or 3 people, and then we go ahead and train other people in their group. Because at first they were intimidated to run or maybe even run a small script on Stampede. It was totally new for them. So one-on-one training sessions were organized with them, and that were very effective in helping them surmount their entry barriers. And once we did that, we figured out that it's not just 2 or 3 people that we have to train. There were like a lot of people in the department who had to be trained. So we developed training documentation, and it captured the basic step right from like how to create a portal account to running the steps in the workflow and what to do if you're stuck at an error. So all that was documented. And after the training and the documentation was done, we were like, why don't we spread this across to other people at international conferences, as in share the experience and spread the knowledge. So we conducted a workshop last year at the IEEE Big Data Conference. And this year also we're doing a workshop on big data management using HPC resources at the same conference. And this project, as I said, helped us reach out to so many non-traditional HPC users, which I wouldn't have been able to reach out otherwise. So I'm very grateful to Exceed and ECSS to give me an opportunity to work on this. So after this project, I will quickly jump to another project that we finished last year. And that project entailed modification of Flash Astrophysics code for optimizing the parallel I/O. So there was no particular PI for this project because it emanated from a consulting ticket. And the main characteristics of this project were how to optimize the file I/O on Lustre file system. And just to give you some more background of the project, so there was a user last year who was blocked from running jobs on Stampede. And we found that the user was running the Flash Astrophysics code using more than 7,000 cores when 2 Lustre servers got overloaded and eventually became unresponsive during the step when they were reading a large file. So we figured out that such intensive I/O activity impeded other users who were trying to use the file system, so the system admin had to block the user. And then after finding out the cause, we told the user to set a particular stripe count manually, and that we considered as a temporary workaround. I say temporary because there's a chance that one could forget to change the default stripe count if the job is run from a new directory. and hence they could be blocked again after overwhelming the file system. So it was suggested that we do an ECSS project to modify the flash code so that a copy of it can be optimized and given back to the user and to other users who would be interested in running at such large scale. So to give you more perspective about the problem scenario, what the user was doing with the job run was, when they were running the flash code, that is, they were reading a restart file just once in a job, and then they were writing multiple checkpoints after every 10 minutes. And as I said, they were running with more than 7,000 cores. The restart file was 250 GB in size, and by default, on Scratch on Stampede, the stripes count is 2. So that was the scenario. And what was happening was, all the 7,000 cores were trying to read the single file, and it was not efficient. So this whole process monopolized the two servers so much that they were unable to respond to other requests and became unresponsive. So my other friends at TAC, Robert McClay, Doug, James, and other colleagues, they had already been experimenting with different stripe counts for reading and writing data to the Lustre file system on Stampede. So I already had some background information from them as to what would be the best stripe count to start with. So after getting the input from them, I started experimenting, running the flash code with different stripe counts. And we started with 2 stripe counts, went on to 40, 30, 40, 60, 80. And we noticed that there is a pattern in the sense that when we are reading the data or reading the checkpoint file, then when you go from 40 to 60, let's say, there isn't such a sharp decline in the time taken for reading the file. However, when we go from stripe count from 40 to 60, as you would notice from the table on the slide, we go from 108.78 seconds to 182.65 seconds. Now, that's a significant increase. So we wanted to choose an optimal stripe count such that both the reading and the writing are done optimally. So we went ahead with the stripe count of 40. That's what we recommended to the user. And then what we did was, after doing a little performance testing with the code, and the checkpoint file that we were considering was 189 GB, and we ran the code on 7680 cores. We basically went ahead and modified the flash code, and what all it took was a simple fix. So we had to add information about setting the stripe count inside the mainly 2 files. One was related to opening the file in the PNet CDF mode, while using PNet CDF, and the other was when they were using parallel HDF5. So Flash is beautifully written for the most part, in the sense that they are already doing collective buffering and various other nice tricks to do optimal I/O. But unfortunately, only this piece was missing. Probably, from what I suspect, is because this is so specific to Lustre, it might not work on other file systems. So I do not know why it was missing, but we just went ahead and added this line there, wherein we are setting the stripe count to a particular number. So the code snippet on the slide was will basically give you an overview of how we did this. And in a sense, my colleague Robert McClay, he has his own high-level library named T3PIO that could have been used in this scenario, but we just went ahead and made this code change directly in there. And that was it. So if you have any questions, feel free to ask me now.
Thank you, Ritu. Any questions?
So, hello?
Please go ahead.
Hi, this is Xu Kwan from Mix. So, Thank you for the speaker. This is really wonderful talk. So I have a question. So is the slides available, because the speaker keep referring to the slides, but for the remote audience, we have no access to the slides yet. Is the slides published on any website or any place I can access the slides?
Sure. I can put the slides online and share the link. And I'm reachable at rauta@staff.utexas.edu. You can email me, and I'll be happy to send you the slides. And I think the session was recorded. Jay, did the slides show up in the recording, though?
They did, although there were a couple of square blocks blocking part of it, but you could basically see them fine. I do know that we collect slides for each of the talks and post them to the symposium website, as well as post the recording to YouTube.
Okay, great.
So probably within the next week or so, we'll have all that squared away.
So will that be announced through the email, or where can I follow up?
So you can send an email to me. My email address is R as in Romeo, A as in America, U as in University, T as in Texas, A as in America, RAUTA@tac.utexas.edu.
Great. Thank you so much.
My pleasure.
Ritu?
Yes?
This is Alan Craig.
Hi, Alan.
Hi. Could you say something about what kind of data were you profiling with the archaeology project, and was that the whole supercomputer project, or what are they going to do with that data now that it's profiled?
So what they were doing was, first of all, starting with the data types, they had just everything from Adobe Illustrator files to HTML files to pictures of different archaeological artifacts, and they were again in different formats like JPEG files, TIFF files, PNG files, etc. They had some LiDAR data that they had collected. So it was very interesting to work with this data set because it was thoroughly heterogeneous. When I said, heterogeneous is enough, but I meant thoroughly heterogeneous because I haven't seen such a diverse data set before. I haven't worked with a data set like that before. So that was about the data set, and what they were doing is after they are cleaning up the data collection, they are developing publication material that's available from their website. And I think it's mostly for scholarly research and further conservation of the data, because once the excavation is done on at an archaeological site, they lose everything out of all the information from there is basically in the digital format or in non-digital format. You lose what was there on the excavation site. So what they're trying to do is conserve the history of the place and study how the city was planned, how the water resources were managed, etc. So things like those are what other scholars working on this data set are trying to study. And the PI and her team are responsible for curating the data and making them available for different stakeholders.
Okay, thank you.
My pleasure.
So Ritu, you mentioned that you had this 5-second delay or staggering for this distributed set of jobs in the Droid.
Yeah.
So why 5 seconds? Why not 3 or 2? So as long as they are not exactly same, it should have worked, or is 5 seconds something special?
No, nothing special, as long as just trying to make sure that the wrapper script created the new job, and then the job was submitted, and then it started. So that was the reason why we had that time period, because it's a very sequential process. I should say pipeline process, because only when one Droid instance is there, a script for that is created, the wrapper script goes to create the next job submission script. So it could have been 1 or 2, but we just picked 5, lucky number. No, I was just joking with that one, Sudhakar. What I meant was, it was not like an experimental value. We just came up with that and it worked.
I have some questions about this, IO optimization. Maybe I'll ask you separately. Maybe I'll give you a call later.
Sure, feel free to do so.
No, thanks.
Thank you. Thank you.
All right. Are there any other questions for Ritu? All right. Hearing none. Ritu, thank you very much for your presentation. Very much appreciate it.